Okay, so let's go back to the physical processes where we left yesterday. I told you that yesterday we have discussed about adsorption and the role of this process in ecotoxicology. And then we started to discuss about balanced transport models. And today we will finish with some indication on how to introduce chemical reaction models into your applications. Yesterday we have introduced the mass balance approaches. And the mass balance approaches is based on the CSTR approximation for modeling. CSTR means continuously stirred tank reactor. So we describe our system as a zero-dimensional system in which everything is well mixed. And we have seen that by employing the balance paradigm, we start always as customary by writing the continuity equation, that is the translation of first principle of thermodynamics or the principle of energy conservation into mathematical terms, and then by applying the CSTR approximation, meaning that we have a system that is completely well mixed, we may define the boundaries of our model by starting the assumption of energy conservation. Again, we write that the accumulation of some kind of substance, for the environmental engineer, I would say toxic substance, is equal to inflow minus outflow plus minus transformation. We said that in the case of the CSTR, we can write down these equations, and in order to understand what this equation tells us, we start analyzing some examples. For example, we start looking what happens in different conditions of the loading function. The loading function is this one expressed here, so the quantity of materials that is entering into the system is equal to the discharge multiplied by concentration of the material into the water that is flowing into discharging water. The concentration on the output is indicated by C, so if we start by the continuity equation, we translate this equation into differential, non-differential equation system. These are first ordinary differential equations. So we have the derivative in time of concentration is equal to the load function minus what goes out from discharge minus what is taken away from the system due to settling. So this is settling velocity times the surface area of the settling time, the settling area times the concentration minus a transformation term that is represented by a K coefficient, that is a chemical equilibrium constant times the volume times the concentration. We have seen some example. If we start looking what happens with a pulse function is represented by an instantaneous discharge of a quantity of materials. This means that the load function here is equal to M when T is equal to T0. This is the delta of Dirac, meaning that this function is 1 when T is equal to T0 and 0 elsewhere. By this load function, by applying this load function, we end up with a solution of the first order differential equation that we have seen in the previous slide, and the solution is the classical decreasing exponential. In this case, we have some example. in which we change the value of the parameters. In particular, parameters are here the quantity of material that is just discharging into the system, the volume of the system, and a lambda exponent coefficient that includes, I recall you, lambda includes all the terms linked to discharge plus settling plus transformation. So this goes to the exponent of the exponential decreasing solution, and the curves that we obtain are at this shape. So in case of a CSTR, zero-dimensional approximation, we have that the concentration changes in time as a decreasing exponential. So after a certain time, the concentration goes to zero. This is what in the past was called a purification by dilution. So we throw a certain quantity of toxic material into the system, and then we expect that the water flowing into the system dilutes this concentration so that in the end the concentrations tends to be zero. A different solution may be found if we analyze what happens with a different loading function. In particular, we shall look at a step loading function. So we have a zero load quantity until t equal to zero. And then we have a starting load L quantity when t is larger or equal to zero. So this is really, this function is a step, meaning that we have zero, and at t equal to zero, we have starting a pollution event. If we look at the solution, this is the formalization of a loading function. And this is the solution with this loading function, what we obtain for the concentration in time is that we have an increase in concentration up to a certain level that we may call a plafond level or a constant concentration. These two examples are very useful because the first one, the example of a pulse function, is what happened into your stream, into your river, into your water body when you discharge all of a sudden in only one event a certain quantity of toxic material. Then you will have this effect of purification by dilution. Of course, purification, it is a joke here. Purification means that the concentration tends to diminish, but of course, toxic substances is being spread around the water body due to water flows. And this second example, the example of a step function, is what happens when you, for example, at a certain point at a certain instant in time, you start discharging a quantity of toxic material into your river. Then what you obtain is that the stream goes into a steady state condition in which you will end up with constant concentrations in time after an initial transient in which you have an increase in concentrations. Then we have seen a last example. This is the example of a pole function in which you have a subsequent exponential decreasing of concentrations. This example is typical, for example, for first flash discharging, for example, sewage systems. In this case, you have, when the discharge starts, you have a peak in concentration due to the washout of the tubes, or washout of the system, or washout of the depurator, purification plant, or washout of the sewage systems. And then, as water continues to arrive, you have a decreasing is an exponential decreasing in concentration. So what's happening here? Again, this is first flash of storm water. For example, when you have a storm event that is impacting onto your sewage system, then you will have a first important washout of the system, which a very large amount of toxic substances are transferred to the system, and then as in the subsequent time instant, you have an exponential decrease of the concentration due to the fact that the sewage are now clean. So this is what happens when you have a storm. The storms begin here. You have a peak in concentration, then as the rain is falling, then you have an exponential decrease in concentration. So this is a washout effect due to rains. We have seen that we have already anticipated by, even if the CSTR approximation is quite a strong approximation, in which we describe our systems as a zero-dimensional system, we have anyhow the opportunity of employing this approximation also for describing more complex systems. For example, in that case, you will employ CSTR networks that can be used to simulate arbitrarily complex systems, but these may be two-dimensional, three-dimensional, going from simple to complex systems. Example, a model network, we may subdivide our estuaries. Let's us focus our attention on a river estuary. We can subdivide our estuary into boxes in which we may consider acceptable the CSTR approximations. This means that in each of these boxes, you will have a constant concentration. And these boxes are all well mixed, constant concentrations. You may also include some kind of spatial differentiation. For example, you may include a two-dimension by, for example, employing layers of upper and bottom CSTR so that you can distinguish between what's happening to the surface of the river or to the surface of a water body and what's happening beneath, under layers. This is, for example, you can download this paper from the internet. It's an application of WASP model in which we try to define, for example, the coastal zone of a large river system. Again, this is the Po River, that is the largest river in Italy. The Po River discharges in the Northern Adriatic area and in Northern Adriatic Sea, and it is of utmost importance defining the coastal zone affected by the discharge of this river. How do we define this coastal zone? In the paper I'm presenting here, Archioli and others, 2005, this is on ecological modeling. In this paper, we subdivide the coastal area, the coastal zone, into a set of boxes. The boxes with a 1 are surface boxes, and the boxes with a 0 here bottom layer boxes. So we are employing a two-dimensional description in which you subdivide horizontally in boxes and vertically in two-layer boxes. And then we describe what happens to the salinity. It is a good indicator of the effect of a freshwater discharge, fresh water coming from a river onto the coastal area. So we describe how salinity varies. We employ a set of CSTR describing the different part of the coastal area or the different part of the sea area affected by the river discharge. And then we include in this description a series of flows that describes how these CSTR boxes interact with the surrounding boxes in terms of water flows. By this analysis, we were able to define with this yellow line the significant part of the area of the sea that is significantly influenced by the river discharge in terms of changement in the salinities. So this is just an exemplification. Now you can employ a CSTR approach, CSTR networks to model even complicated water bodies or water system, water ecosystems. Now let's switch to the second mass balance approach, that of a plug flow reactor. As we have said already, the plug flow reactor are a system in which you imagine that there is a constant flow of water in a predominant direction. So this is the approach that you may employ when you need to describe a river, for example. So again, we concentrate on an elementary section of the river. The section has a thickness that is delta x, so infinitesimal x thickness, and x is the coordinate that is describing the distance from the initial part, from the starting of the river. Again, we start from customary continuity equation. We may write that accumulation in the infinitesimal box is equal to inflow minus outflow plus minus transformation. How do we translate mathematically? We write that the elementary volume times the variation in time of concentration C. So this is again a first order reaction, is equal to what goes in, so the inflow multiplied by the section of the river. A represents the section, the river section. So A, it is B times H, minus what goes out from the river, J out, again multiplied by the section of the river. So inflow minus outflow. So these are densities of surface density of flows. So if you multiply them by the area, you obtain the total flow across the area of the river. And then we include a term of chemical reactions. Sorry, one moment, please. Okay, sorry. Accumulation, variation in time of concentration is equal to what goes in minus what goes out, minus what is transformed through reactions in general, that may be chemical or physical reactions. So if we explicitate the flow densities, we may write that the J in, so the flow in is equal to the speed of the flow, to the speed of the stream U times the concentration in the flow. U may be calculated as the ratio between the discharge and the section of the river. J out is equal to the concentration times velocity plus velocity times the changement in concentration along the x-axis multiplied by the infinitesimal delta x. If we put all these things together, we obtain a partial differential equation in which we have a derivative in time of concentration C is equal to minus the speed of the flow times the variation in time, variation along the x-axis, so along the stream of concentration, minus a term of that describes the effect of transformation. In steady state, as it is customary, we may write that the variation in time of the concentration is equal to 0, so we are in steady state, so we are at the regime now. And in this case, the solution of a differential equation, as you may imagine, is the classical decreasing exponential curve, in which now we have a dependence in the exponent from the horizontal coordinate, so from the distance from the starting of the river. For the mix, yes.
Please, can you explain again well the expression for G out, for the output?
Yes. The J out is the density of flow of the concentration of the substance outside of the infinitesimal element. The G in is equal to the speed of the flow times the concentration, and the speed of the flow is discharge divided by this section of the flow, while the J out is equal to the speed of the flow times the concentration of the infinitesimal element plus a term that describes the fact that the concentration decreases along the x-axis. So we employ a term that describes what happens due to the fact that along the flow, along the direction of flow, we have a decrease in concentration that is proportional to the distance from the inlet. What it is not clear in this?
Yeah, it's okay, sir.
Okay.
Thank you.
You are welcome. You put all these together, in steady state, you find the exponential decreasing solution, in which you have that the concentration decreases along the direction of the flow. I remember that this is a plug flow approximation. So here you're not applying CSTR. Instead, you are applying the fact that there is a constant flow in a dominant direction, that is the direction of the river flow, X. Okay. What happens in mixed flow reactor? This is typically if you want to describe turbulent transport in a river. Again, we start by the customary continuity equation, and we write that the variation in time of concentration C times the elementary volume is equal to what enters into the volume minus what exits from the volume, all this multiplied by the section of the river or the section of your flow, minus a term of transformation that this time depends on the average value of the concentration, because here we do not have a preferential decrease in one direction. If we put all this together, and we may define that the flows is equal, inflow and outflow as well, is equal to the speed of the flow times the concentration minus a term that is takes away from the flow some quantity of material due to eddy diffusion, so you include an eddy diffusion coefficient, and you multiply this for the variation in space of the concentration C. If we put all this together, so we are simply using this equation and recalculating this, we obtain this partial differential equation. in which we have that the variation in time of concentration C is equal to a term that is dependent from the speed of the stream multiplied by the variation along the stream direction of the concentration plus a factor that takes into account the fact that there is eddy diffusion processes, and this is accounted by a coefficient E, that is an eddy diffusion coefficient, multiplied by the second derivative in the spatial direction of the concentration C, minus the customary transformation term. As always, steady state. This means that we assume that we are in a regime now, so the concentration in time is not varying, but instead it is varying in space. In steady state, the solution of this equation comes by this, and you probably may know, sorry, but in steady state we have these partial derivatives differential equation, but it is not first order anymore. In the case of eddy diffusion, you have second order derivatives of the concentration in the spatial directions. Okay. I am going quite fast because I assume that you have already seen this is a hydraulics class. And if you have followed an hydraulic class or solid transport class, you should have already seen all these equations. Now I'm just recasting this equation in the context of ecological modeling or modeling of environmental systems. Beside the assumption of mass balance, we may instead concentration on mass transport. So we are simply now trying to understand what happens to substances that are transported by water. This process, of course, you know it, is called advection, and advection is transport along with the fluid. There is no concentration variation in the case of the transport. This is why we do not need to make a mass balance here, but instead we study mass transport. So we have different approaches. The first approach is the approaches of mass balance that bring us to the CSTR, PFR, or MFR approximation. Instead, in the case of no concentration variations, we are trying to describe what's happening to substances that are moving with the bulk of the fluid. The two main processes we shall consider here are advection, that is transport along with the fluid, but also diffusion, that is moving concentration of gradients. So if we take these two processes together, the collective process is called dispersion, and dispersion means combination of advection and diffusion. How can we model mathematically this thing? So we are trying to model transport along the flow direction, which dominates, and negligible changes in concentrations. We start by, again, considering an infinitesimal volume of water body of your system. So you have a small dx, that is infinitesimal quantity in the x direction, times the epsilon, that is infinitesimal quantity in the epsilon direction, and the z, that is infinitesimal quantity in the vertical direction, z. Again, now we start from customary balance equation, customary continuity equation. Here we consider only input and output. We do not consider chemical reactions because this would complicate things further, but we will see later how to include them. Okay, so we shall write the J1, J2 input and output. Sorry. For the input, we write what we discharge times the concentration is the flow in, and you explicitate it by writing that the concentration times the speed of the flow times the section through which the water is flowing. J2 is the same, but instead we shall make a kind of Taylor expansion of the quantity Cu, so this concentration times the velocity. If we make a Taylor expansion in the x direction, and we stop at the first order, then we may write J2 depending on what comes into the system plus what it is moved away from the system along the x direction. If you make the difference, J1 minus J2, so we are really writing the accumulation quantity here. And let us only consider one direction for simplicity here, so along the x-axis, we end up by writing that the variation time of the concentration C times the infinitesimal volume, so this is V times concentration, volume times concentration, so this is a mass term, is equal to J1 minus J2 times multiplied by the section to which the flow takes place. And then, if we put these things together, and if you generalize it in 3 dimensions, we end up with this differential equation, which we have maybe new to you differential operators. This is the divergence of the vector V. V is a vector representing the speed of the flow. Note that we are in 3 dimensions here, so this is a 3-dimensional vector, plus the scalar product of the speed, vectorial speed, times the gradient in concentration. The first part describes the time change in concentration. This part describes the concentration, the variation in concentration due to compression and expansion of the fluid. And the third part is the real advective term, the term we are interested on. And if we consider uncompressible and conservative fluids, so fluids for which the divergence of the speed, the divergence of the vectorial velocity is 0, and if we consider steady state condition, then we may include these 2 approximations, and we end up with this partial derivative differential first order differential equation, in which we have derivatives in time and derivatives in the spatial coordinate x. So what we are describing here, we are describing a quantity of material, but at a certain point it is found in the point x1, and then this material is moved with the bulk of a water movement to position x2 at time t2 and to position x3 at time t3. So you do not have changing concentration in the bulk water movement. Instead, you have concentrations that are moving along one direction. Okay? Now, we can go a little bit more in detail into the physical processes of molecular diffusion. This is important because it allows us to understand what are the meaning of the various diffusion coefficients that you may find in transport models. Here we are dealing with models that describe transport of substances in water bodies, in water ecosystems. The first assumption is that of isotropic Brownian motion. So we have chaotic motions in all the directions. This is very important for vertical transport. For example, this is what what causes stratification or sedimentation, and it is the basis for mathematical formulation of the turbulent diffusion. This is why we need to introduce this new model, this approach, because we want to end up with a complete transport model that describes also turbulent diffusion, that is the most complicated diffusion processes that we may conceive. How do we do that? We start by analyzing an infinitesimal volume. We may subdivide this volume into two subparts, subvolume A and subvolume B. We may imagine that we have only material in the first block A, and then we can imagine that this material moves by diffusion processes, and for now we do not focus too much on what these diffusion processes are, but we know that the tendency of smoothing gradient may be described by the fact that you have material that is passing from one subvolume to the other. The idea is that of employing a probabilistic approach of the so-called random walk. Again, we apply accumulation equal input minus output, conservation. Let's look along the x-axis, what may happen. We may write that the variation in time of concentration or accumulation time the volume, infinitesimal volume, is equal to what goes in minus what goes out. Please note that we are neglecting again transformations here. What goes in minus what goes out is a density of flows multiplied so for the section of the flow. For example, if we consider one direction, we obtain the first fixed law that tells us that the flow in the direction x is equal to minus the diffusion coefficient in the x direction times the changement in concentration along the x. If we put all these together in one dimension, or we obtain again a partial differential equation, which we have a first order derivative in time and second order derivative in space, and you obtain the so-called second fixed law, in which you have that the variation in time of a concentration C is equal to the diffusion coefficient, and this is diffusion in one, is the collective diffusion coefficient multiplied by the Mabla. This is another differential operator. These represent second order spatial derivatives, this operator. So that we may say that in 3 dimensions, this is for the first dimension, for 1 dimension, in 3 dimensions, the generalization tells us that variation time of the concentration C is equal to the diffusion coefficient D, but in this case it is a 3-dimensional diffusion coefficient, times the Mabla operator of the concentration, that is the second order derivative in space of the concentration. What is the solution? The solution of this differential ordinary partial differential equation. We assume that we have a mass m, quantity of material m in the starting point, x equal to 0 and t equal to 0. By applying this initial condition, we obtain a solution that tells us that the concentration changes in time with a bell-shaped curve as it is customary. We may arrive to the same observation by simply applying a probabilistic approach. So we may rewrite the flows in terms of what the quantity of material in A multiplied by the probability of passing from A to B divided by the section. In the other direction, the quantity of material in B multiplied by the probability of material passing from B to A divided by the section. If you multiply and divide by the square of the x, then you end up with this equation. And this equation allows you to understand that the dispersion coefficient has to do with the probability of matter passing from moving along the x direction. In particular, the shape of this curve is like this one. For example, the blue one, it is when you have a timing of 10 minutes. So after 10 minutes, you have a gradient smoothing like that. After 1 hour, you have a reddish gradient smoothing. After 5 hours, you have a quite a larger gradient smoothing again. Here, for plotting these curves, we have assumed that the diffusion coefficient is 10 to the minus 3 square centimeters per second. Okay. We may complicate a little bit further our model. For example, if you want to describe turbulent diffusion, that is what typically happens in the outlet of a river, in a bay, for example, then what we do is we consider average values of speed, and we consider that these average values of speed may oscillate around. So the real speed, ut, may oscillate around the average value of speed. You do the same for concentration. So what we are including here are some stochastic perturbation on the state variable describing our system. Do you remember when we said that if we want to include random processes, we shall include some kind of stochasticity in terms of probabilities? So we make a changement of the vector of the velocity, the speed vector, by saying that the speed vector is equal to the average speed plus a perturbation. Same for concentration. Concentration is equal to the average concentration plus a perturbation of the concentration. If we put all these things together, again, we consider uncompressible fluids, otherwise things might get very complicated. You obtain a net advection of a substance due to turbulent diffusion. And the net advection of a substance due to turbulent diffusion is exactly the speed times the concentration, or the perturbation in the speed times the perturbation in the concentration, that is equal to minus a diffusion coefficient. This is one dimension, so in the x direction, multiplied by the gradient or changement of concentration in the x direction. In 3D, we obtain a convective diffusion equation in which D represent the terms that describe the diffusion conditions. In particular, D in this case, it is a tensor, so not even a matrix, but it is a more than two-dimensional set of values in terms of diffusions. Please note that the values of the diffusion coefficient. In particular, diffusion coefficients are in the smaller diffusion coefficients are those of molecular diffusion. Molecular diffusion is due to temperature. So the diffusion coefficient, that is generally much more larger than the molecular diffusion coefficient, depend on space scale, and it is anisotropic. This is why we need to include the tensor here. So that I found this table very useful because this gives you an idea of the ranges of molecular diffusion coefficients. For example, if you express diffusion coefficient in square meters over seconds, you will have that smaller diffusion coefficients are those of thermal diffusion, so temperature density, heat capacity, and so on. Why, if you go to molecular diffusion, that is a typical diffusion mechanism by which proteins or salts and gases in water are displaced, then you have value of the diffusion coefficients that are in the range 10 to the minus 10, 10 to the minus 8. If we go to eddy diffusion, that is typical for flow regimes, but depends on the flow regime and on the spatial scale. For example, for stratified waters, bodies like lakes and oceans, you have values of the diffusion coefficient in the range of 10 to the minus 6, 10 to the minus 4. Sorry, today it is a nightmare, the telephone calls. And then if you consider eddy diffusion in, for example, surface water bodies, river, creeks, and so on, so these are the conditions in which you have the largest diffusions coefficients, then you will have diffusion coefficients in the range 10 to the minus 2 and 10 to 2. So the molecular diffusion, so the diffusion coefficient goes how spread the Bell curve is. In particular, the spreads, so the larger of the Bell is equal to 2 multiplied by the square root of the diffusion coefficient multiplied by T. In particular, if we consider a T of 1 hour, and for different value of the diffusion coefficient, what I am expecting to find, it is a progressive smoothing gradient. Okay, so we are looking at what happens at the concentration at X, in particular at 0, you have a maximum in the beginning, and then you have a smoothing gauge bell-shaped curve. And this happens after 1 hour, so you leave the system 1 hour to move materials through diffusive processes. Okay, now let's put all that we have learned together in order to obtain a dispersion model. So it is an advection plus diffusion model. The effects of velocity profiles can be modeled using, for example, Fick's law. In this case, we may rewrite our continuity equation and we may recast our differential equation. This is a non-linear partial derivatives differential equations. In particular, this is made up of two terms. The first term that is an advective term that depends only on the speed of the stream of the current times the gradient in concentration, minus a diffusive term that is calculated as the divergence of the diffusive coefficients tensor multiplied by a scalar product to the gradient of the concentration. If you consider these two terms together, you obtain a dispersion model. Let's see what happens in 1D, because in 3D it becomes quite complicated, the solution and also to draw the curves in one dimension, you obtain that the variation in time of concentration is equal to minus the speed of flow multiplied, and this is a scalar product because u it is a vector, multiplied by the gradient concentration along the direction x plus a diffusion coefficient multiplied the second order derivative in concentration. So you see this is a second order partial derivative differential equation. The solution is this one, and if we draw this solution, for example, for a diffusion coefficient of 10 to the minus 3 centimeters per second, and for a flow stream speed of 0.01 meters per second, for example, after 10 minutes, you will have this kind of change in concentration along the X section. After 1 hour, you will have that material is moving due to advective processes, but you will have also that the bell-shaped function is moving due to dispersion processes. After 5 hours, you will have that the material has moved away from the starting point and diffused into the surrounding space. For example, you can also look at what happens in time. Let us focus at x equal to 0, so to starting point of the flow, and let's look at how concentration changes in time. For example, for a diffusion coefficient of 10 to minus 3 square centimeters per second and a speed flow of a stream of 0.01 meters per second, what we obtain, it is a curve like this one, the last one. So you have a decrease, an exponential decrease in concentration due to both the fact that the material is moving by advection due to the transport of a bulk material with the water, and that the concentration is decreasing also due to diffusion, due to diffusive processes that are described by the diffusion coefficient D. Okay? Now let's go back a little bit to a model that we have already seen, the physical process interface transport model. This is another way of describing material transport. In this case, the approach is slightly different because we are considering two portions of the system, a gas portion and a liquid portion. I recall you that this model was employed in order to introduce the transport, the exchange phenomena between the atmosphere and the hydrosphere. So what is moving from the liquid to the gas. If you write, for example, again, the flows, in the liquid phase, if you want, in the liquid film, JL is equal to KL, that is coefficient of an equilibrium coefficient of the transport in the liquid film, multiplied by the difference between the concentration in the interface and in the liquid phase. So we differentiate the concentration in the film from the concentration in the bulk of the liquid. For a gas portion, again, you have the same by employing partial pressures instead of concentrations, but you know that we may switch between pressures to concentrations by employing the law of ideal gases. You know that we may find a relationship between concentration and partial pressures by Henry's law. You know that if we are in steady state conditions, so condition in which the flow in one direction is equal to the flow in our direction, in the inverse direction, so that you can simply employ J for describing this flow. In this case, you may write that the solution, by putting this together, is that the flow or the current is equal to a difference between partial pressure in gases phase divided by the Henry constant minus concentration in the liquid phase, and this quantity at the numerator of this fraction plays the role of potential difference. So this is like the Ohm's law of electricity, which you may recall, but the Ohm's law of electricity tells you that the current is equal to variation to the delta V, so the potential variation divided by what? By a resistance. So you have a driving force that is moving material from the liquid phase toward the gas bulk in a Ohm's law-like approach. In this case, the driving force, and if you employ the Ohm's law description, this is an analogy with resistors in series. I recall you that we have already seen this model. In this case, the resistor in series is represented by these two terms. The first term of the resistance, but this is resistance in the liquid film, in the gaseous film, and plus another resistor contribution, that is the resistance to the transfer in the liquid phase. You know, the physics is always the same because the processes are very, very analogous in terms of microscopic processes, so that from the point of view of the macroscopic physics, the results are exactly the same for the law of Ohm for electrical circuits as the law of physical processes of interface transport of material at interfaces. These end up more or less what you are supposed to know concerning our way of modeling transport processes. Transport processes are made up of two terms, an advective term and a diffusive term, and then we have been able to derive up to here a very detailed description of the advective term and of the diffusive term. The important things to remember is that the diffusive terms are dramatically dependent on the diffusion coefficients. In reality, what we are hindering all the complications into the diffusion coefficients. Okay, so now let's go forward to the last model we shall employ for describing physical processes, chemical processes, that is the model of reaction kinetics. So how do we describe chemical transformation into my ecosystem? I recall you, this is a matter of introducing some notation. You may write chemical equation by writing that the stoichiometric coefficient small a multiply capital A, that is the concentration of substance A, plus stoichiometric coefficient small b time capital B, that is the concentration of substance B. After a chemical reaction, they get transformed into two other molecules, so C and D, whose proportion are described by the stoichiometric coefficient small c and small d. I recall you that all of these come from the law of mass action. You may recall from your chemistry classes that the law of mass action tells us that the variation in time of the concentration of a particular substance that is participating to a chemical process is equal to a constant minus k, a constant equilibrium that is called the equilibrium constant, time the concentration of substance A elevated to alpha, time the concentration of substance B elevated to beta, time the concentration of substance C elevated to gamma, time the concentration of the substance D elevated to delta. So this is a way of translating this chemical writing. This is a chemical way of writing chemical equation into a differential equation in which you describe variation in time of one of the concentration. And we know that by the law of mass action, we may write that the variation in time of concentration, one of these concentration is equal to these quantities, where the number alpha plus beta plus gamma plus delta is called the order of the reaction. Okay, this is the most, one of the most general way of describing chemical reactions, but as we have said, and as we will see in the following classes, in the following lecture, often the chemical reaction depends on just one substance. In general, we call it the substrate. For example, if we have just one substance, let's say the substance C, the law of mass action may be written by saying that the variation in time of concentration C is equal to minus the equilibrium constant K times C elevated to N. If we consider first order reactions, that is all in general acceptable, especially as a first approximation, as a first approach, when you want to describe a chemical reaction happening into environmental systems, then you end up with the customary first order linear differential equation in which you have that the variation in time of concentration is again equal. Always the same story. Solution is a decreasing exponential in which you have a starting concentration C0, but it is reducing exponentially by a term depending on the equilibrium constant of a reaction and of the time. In general, we know that chemical reactions are dramatically driven or governed or influenced by temperature. And this is of particular concern when dealing with ecosystems, which, as we have said, temperature is an important external forcing function or external driver that changes significantly the behavior of the system. In that case, we include the temperature dependence by making the equilibrium constant K dependent on the temperature, and we do that by an Arrhenius-like approach. So we say, we generally model that, in our model we say that the equilibrium constant of the chemical reaction at temperature T is equal to equilibrium constant of the chemical reaction at 20 degrees multiplied by this Arrhenius term, that is a theta elevated to the difference of the temperature from the reference temperature 20 degrees. I am sure that you have seen all over these Arrhenius relationships, but now I am particularly fond of going a little bit more in some detail towards some very particular chemical reactions, chemical processes, what are the so-called enzymatic reactions. Enzymatic reactions are of particular relevance for biological systems because 99% of the chemical reactions that happen in biochemistry are enzymatic reactions. Enzymatic reactions are reactions that not only depend on the presence of a substrate, instead they depend also on the presence of another molecule that is called the enzyme. Enzyme is a molecule that somehow fosters or induces the chemical reaction. By employing our modeling of a chemical reaction, we may write that the substrate plus the enzyme is transformed by a forward reaction whose equilibrium constant is K1, so that the ES star, that is the activated complex, that is a kind of chemical bonding between the enzyme and the substrate, is created, This is a two-way reaction, so as soon as you have an activated complex, then the complex may be deactivated, so that there may be a splitting from ES star to S plus E, and the reverse reaction described by the second equilibrium constant K2. And then the third part of the reaction, that the part that goes from the activated complex ES star to the product, is represented by this third equation, whose chemical reaction, whose speed is represented by the equilibrium constant K3. If the activated complex is in general unstable, meaning that when you have an ES star, as I told you, there is a high probability that the bond is split back, so that you have a kind of steady state condition in which you will find out with constant concentration, due to the fact that there is an equilibrium between the two reactions, the one proceeding forward, and the other one proceeding backward. So the activated complex is unstable. The enzyme does not disappear during the reaction, so that at the end of the reaction, so the totality of the enzyme is always what you had in the initial part of the reaction plus what you have transferred to the activated complex. Let's apply now the law of mass action, as we have seen. So let us translate these into differential equations. The variation in time of a substrate S is equal to minus K1 times the concentration of E, the enzyme, and the concentration of substrate, plus the reverse actions, but depends only on the concentration of the activated complex. Then we need another equation describing the dynamic of the activity complex. In this case, we have that variation in time of the concentration of the activated complex is equal to K1, formation of the activated complex, minus K2, that is deactivation of complex, plus or minus, again, because there is a minus K3, that is the fact that represents the fact that the activated complex is consumed in order to end up with the product P. And we may write then the third equation, like this one. Again, in steady state, we consider that the variation in time of the concentration of the activated complex is 0. And by this assumption, we end up with the solution. Again, please look. So yeah, if we put all together these three differential equations and these starting condition due to a steady state assumption, if we put all these together, you end up with a solution. That is the one I have represented here. So you may write that the variation in time of the substrate is equal to minus a constant mu max, what we may call the maximum growth rate, if you want, times this quantity, that is the concentration of the substrate divided by Ks, that is the semi-saturation constant plus, again, the concentration of substrate. This model is called the Mcesy-Menten model, and it is by far the most largely applied model in modeling ecosystems, or, if you want, biological processes. Why this? Because, as we have said already, and as we will say more in deep in the next lectures, biochemical reactions are reactions that are well modeled by enzymatic processes, because they depend, these biochemical reactions depend by the presence of a very particular enzyme activating mechanism. That is that of the activated complex. And in particular, for example, if we are going to employ this kind of model to describe, for example, the growth of very simple organisms like bacteria, or if you want algal growth, because for us, primary producers bacteria are algae, and as by now it should be clear to you, you are very interested in modeling algal dynamics. In this case, who plays the role of the enzyme? The algae itself, because the more the algae presents, the more will be the production, because this very particular living organism, they replicate by splitting in two. So at every generation time interval, you will have a doubling of the number of cells due to the splitting process. If we look in detail at the Mcesy model, this is the classical saturation model. Here we describe the speed of a reaction, V, as a function of the concentration of substrate. Okay, so the speed of the reaction increases as the substrate in quantity increases, but does not grow indefinitely. Instead, there is a kind of saturation behavior in which you have an increase on the chemical reaction speed up to a limit that is called the maximum reaction rate, maximum possible reaction rate. The maximum possible reaction rate depends on the particular organisms and on the context in which these organisms are embedded. This is of utmost importance in medicine. I forget to tell you that the K constant is Ks, that is called the semi-saturation constant, represents the concentration of the substrate at which you have half of the maximum speed of reaction. This is why this constant is called the semi-saturation constant, because after when you are at Vmax, you are in saturation. So you cannot not increase anymore the speed of reaction. This means that the carrying capacity of a system has reached its maximum value. In this case, I tell you that this is very of utmost importance, especially when we are dealing with pharmaceuticals, because the large majority of our pharmaceuticals act by changing the condition in which enzymatic reactions take place. We have two ways of changing the condition. First one, inhibition. So in inhibition, you have a slowdown of a reaction, and so you may have inhibition in case of non-competitive inhibitors. So, for example, if there are covalent allosteric bonds that tends to render the reaction more difficult to happen, or you may have competitive inhibition in which there are other chemicals that take place into a reaction and that has an overall effect as the effect of slowing down the reaction. Then the other way of changing the reaction condition is that of induction. Induction means increasing the speed of the reaction. And you have induction if you have an increasing enzyme number. So, for example, by induction of gene expression of a various enzyme in biology is one of the mechanisms. Or if you have an increase an enzyme affinity to the substrate. So this has to say as lowering the energy of activation of the activated complex. These are different ways of moving the Mcesy model are represented by the arrows. These arrows, the red arrows, non-competitive inhibitors tend to decrease the maximum speed of reaction, while competitive inhibitors tend to make the reaching of a semi-saturation constant more fast. So for competitive inhibitors, what is happening is that the Mcesy model is moving in this direction. Different is the case for induction. For induction, you have, for example, an increase in enzyme number may increase the speed of reaction. So this is why you have this is why we call induction. Or an increase in enzyme affinity to the substrate is a way of pushing back the Mcesy so that the saturation constant, the saturation value is reached more quickly. So in case of inhibition, competitive inhibition, you reach the saturation much later. In case of induction, for example, in case of increase of enzymes affinity to the substrate, you tend to reach the saturation condition much quicker. It is interesting to give a look to the so-called lock and key model for enzymatic reaction. For example, if we consider the substrate by red triangles, we may describe the effect of the enzyme like a perfect molecule that sticks perfectly to the substrate, so that the activated complex, in this case, I recall you this enzyme plus substrate, the activated complex, finds itself in a kind of steady state equilibrium in which you have formation, activation, and deactivation of the complex. In the case of competitive inhibitors, is the case in which you employ, for example, pharmaceuticals, which have a shape that is similar to the substrate, so that this object can, for example, occupy one enzyme. So in practice, this is reducing the number of available enzyme for the reaction. In the case of uncompetitive inhibitor, you have particular molecules that sticks to the enzyme, making the enzyme permanently unavailable. Again, here we have a steady state condition again, in which the activated by competitive inhibitor complex deactivates and reactivates again and finds itself in a state of steady state. In the case of uncompetitive inhibitors, there is no such steady state condition, but this simply means that the enzyme is taken away from the pool of molecules that may foster the reaction. There is a third case, that is the case of non-competitive inhibitors, and this is a case in which we have molecules or chemicals that simply destroy irreversibly the enzymes. So this is a way of changing in an irreversible way by destroying the enzymes and making the enzymes not available anymore. Okay? Okay, before concluding the lecture of today, I would like to give you some practical example of mass balances, and we will see by this how this consideration help us into understanding the important role of biogeochemical cycles. Biogeochemical cycles involve several different types of processes. Let us start as customary by giving an example of limnology. So we look at a lake. Lake, you have a water body, so water column, and you have sediments. I recall you that sediments play a key role in the biogeochemical cycle. In the case of lakes, for example, we may imagine that we have phytoplankton growing in the lake. Phytoplankton is consumed by zooplankton. Zooplankton is consumed by fish. The currency of this model is nitrogen, for example. So we consider nitrogen in phytoplankton, nitrogen in zooplankton, nitrogen content in fish. We have water inflow and water outflow from lakes, because lakes are seldom completely closed systems. And then there is interactions between the water column and the gas or the atmosphere, which you may find, for example, nitrogen in gaseous forms. We know that phytoplankton growth depends on the presence of ammonia and nitrate. In particular, we do not consider nitrate because, as you know, nitrate very quickly oxidates to nitrate. Is absolutely true, when you are in a condition typical of living systems. So how do we do balance? Try balancing nitrogen currency by explicitating the flows of nitrogen because these two various compartments. Please note what here we are employing. We are in conceptualization phase, and we are employing the box and arrows model in order to describe state variables as boxes and processes as arrows. We are giving a spatial differentiation of the system, in particular in the vertical part, by separating the atmosphere from the hydrosphere from the sediment parts of the benthos of the system. If we look at the processes, again, I know it is boring, but it is always the same story. We employ the most general principle that we know today, that is the principle of energy conservation. We write that accumulation of something is equal to input minus output plus minus reaction. How do we employ this description into biogeochemical cycles balancing? We may simply write a differential equation in which we say that the variation in times of a nitrogen in the form of nitrate, so here we are modeling the state variable nitrate, is equal to what goes in, Q, in terms of nitrogen in the form of nitrate, minus what goes out, so the flow out in terms of nitrogen in nitrate going out. So input, inflow minus outflow, plus what? Plus we may include the several, some transformation processes. In this case, we may include the nitrification process. So reduction of nitrate into gaseous nitrogen. Of course, this depends. It is a quota that takes away from the reaction terms nitrate and put it into gaseous nitrogen, or plus nitrification, so oxidation of nitrate, that it is a way of including oxidative processes that transform nitrate into nitrate. And then we include a set of other processes that we also may know biological transformation processes. In this case, this is predation, or assumption, more precisely, assumption of nitrate for phytoplankton growth. So we have a term, transformation, that depends on the speed of the process, of the growth rate. This parameter is called the growth rate mu times a calibration coefficient alpha multiplied by the quantity of algae or phytoplankton. So this is a state variable describing phytoplankton. So this is consumption of nitrate due to phytoplankton growth. Now this is really a way of putting in practice balancing of biogeochemical cycles. This approach is very general, so general that we may we may employ mass balance that are simply on the basis of energy and mass conservation, that are the basic physical constraints in this case. You remember what we said about constraints? Constraints allows us to reduce the number of degree of freedom of the system. So, for example, we may describe the quantity of biomass of certain species. For example, this is a sea water ecosystem or brackish water ecosystem. And the biomass of one of these species in my ecosystem is increased due to the process of consumption, of food consumption, and it is decreased due to the process of predation by upper trophic levels. Then we have some more flows that might be of interest, especially if you are dealing with sea ecosystems in which there is a significant anthropic impact. For example, you may include catches. So these are catches by fishing activity that takes away part of the biomass, and or net migration exports. So this is due to the fact that some of these kids here possess free will, so they may decide that they do not like to stay here and they prefer to move somewhere else. And then you close your balance by considering the fact that these creators generally perform respiration, so they some of the biomass may be consumed for respiration, and you may also include, you shall also include that these creatures typically go to the toilet, so they excrete some of the material, so you have a backflow to the detritus by excretion, exhaustion, or unexplained mortality. For example, these creators may die for some non-immediately explainable causes, for example, diseases or dramatic changes in the environmental condition. So, according to the basic physical constraints, you may always be ready to apply our continuity equation description in terms of mass balance. And by building this kind of approximation, as I showed you, you may end up with very complex models describing very heterogeneous systems. Again, this is the networks model of the Paluda de la Rosa ecosystem, that is mean annual model for year 2001. This is a model describing a true real condition, what is a portion of the Lagoon of Venice, in which we have tried to describe the effect of various activities or scenarios on the quality of status of ecosystem. Please note that the mass energy balance paradigm is what the environmental engineer typically employ when he's doing life cycle assessment. From the cradle to grave, in this case, you may quantify all these flows, and then you shall end up with a balanced network by simply employing the mass energy balance paradigm. Okay, I am sure you are very tired, so we stop here for today. And I wait for your questions. Otherwise, we shall meet next Monday at 10 a.m. Down the time. Is it okay?
Okay, sir.
Yes, sir.
Do you have any questions? I stay here 5 minutes more, and if you have any questions, I am ready to answer to your questions. And otherwise, I